This is chapter 7, or excuse me, this is chapter 10, problem 7, and this is the one where you have a ball attached to a spring with an unstrained length of 0.2 meters. So I'm going to go ahead and get a picture up here where we have a spring, and then we have, let's see, spring is held by the other end, and the ball is whirled around the horizontal circle at a speed of 3 meters per second. Okay, so we actually have it going around in a circle, so I'm going to go ahead and label that, and this is going to represent right here my spring, and we've got our 0.2 meters is what we have for our unstrained length of the spring when the thing's hanging off of it, and now we have an additional 0.01 that it stretches when we whirl it around in the circle. Additional 0.01 for a total there of 0.21 meters for the radius of our circle. So the idea being here, we're swinging it around, and we have our 0.2 that it would be stretched, and then our extra as we swing it around of 0.01. So that's the radius of our circle as we swing this thing around our head. So picture Mario ball on the string, except replace the string with the spring, and you have the picture that I'm attempting to convey here with our radius being 0.201. So that's our radius r. And now they ask us, the spring remains nearly parallel to the ground. Oh, we've got that. By how much would the spring stretch if it were attached to the ceiling and the ball allowed to hang straight down motionless? So here we have the ball here, and we want to know this distance. Okay, if we're allowed to hang straight down motionless, what would that be for this spring? And I believe if we can get k here, we can figure out what that distance will be. So let's go ahead and start, since we're moving around in a circle, and sum our forces along the radius. That'll be equal to mv squared over r. We only have one force along the radius. Instead of tension, this time it's going to be the force of the spring. So force of the spring equals mv squared over r. And I can replace this with a k, and then I could write x, but I'm just going to go ahead and put in my 0.01 because that is the amount that I have stretched extra. That's my x for my force. Because remember, the 0.2 is when it was unstrained. Our extra is our 0.01 when we spin around. So that's the part that's accounting for the force of the spring back in towards the center of the circle. So we have a 0.01 here for our x equals mv squared, and our r I talked about already is 0.21. And let's see here, do we have anything else that they gave us? Oh, they gave us v. Oh wow, they gave us lots of information. So they also gave us v. So I'll go ahead and plug that in, and we'll solve then for k, because the one thing, two things will stay the same when we go from here to here. One thing is k, because it's the same spring, and the other thing will be the mass, because it's the same sphere hanging off the spring. So m times 3 meters per second squared, 0.21, and I'm going to solve for k. And yes, I'll still have an m in my equation. Hopefully that'll be okay. We'll find out when we substitute in. So we'll have 9 divided by, oh, it's not working. Just a second. I need to clear my program. I need to reset the virtual calculator's memory. There we go. All right, so now let's take 9 divided by 0.21, because that was my 3 squared divided by 0.21, enter. And I'm getting 42 something, divide by the 0.01 on the other side. I get some huge number. You could do this, by the way, with the variables staying in there. So 4285 times m, and I should really have units on that. Let me figure out what the units are here. So meters squared over seconds squared over a meter. Move that over squared. Should be k should be a newton per. It's not working out. Oh, but units of m. I'll just leave that as some constant out front. So I'm dropping the units just for speed purposes here. So 4285, call it 4286 times m. So that's my value for k. So now I'm going to go look at that other spring, and I know I want to find, let me make sure I got the right thing here, by how much would the spring stretch if we're attached to the ceiling and the ball allowed to hang straight down. So it's now motionless. They say it's motionless. So when I sum my forces in the y direction on this guy, I'll get 0. And I should have force of weight going down, and force of the spring going up. So force of spring minus force of weight equals 0. So I'll have K times whatever this new X is, which is what I'm trying to find, minus mg equals 0. And I'm trying to find X, so let's go ahead and solve for that. So I'll have Kx equals mg, and X equals mg over K. And I've got a value down here for K, so let's plug that in and see if it worked out. So X equals mg divided by 4,286. And again, I've just dropped units for clarity and speed's sake, times m. On a free response question, don't do that. Put the units on there, or better, just leave the variables in here until you get to the end. That would work as well. And then x would equal, the m's will cancel, so it should be 9.8 divided by that. That does not seem right, but I guess we'll find out here in a minute. 9.8 divided by 4285.7, or 42, what I call it, 4286. 4286. There we go. That seems like it's going to be awful small, but that could be right. I don't know. 0.0023, and that should come out to be in meters. And let's see what they got. Problem 7. 2.29. They have 2.29 times 10 to the negative third. And I have, oh, I miscopied. 0.00228. So, oh no, that works. So 10 to the third. 1, 2, 3. Yep, so I've got 2.3 times 10 to the negative third. Same difference, so it does work out. If you take a look at the key, feel free to come in. If you take a look at the key, they went ahead and just left the variables in. Their m's do cancel, and they end up doing the same type of operation that we did at the very, very end here. The very, very end, and they get their 2.29 times 10 to the negative third. So that does work out. If you have any additional questions on this one, just stop by. Thank you.